Good everyone, today we'll be taking biochemistry. We'll be looking at the biochemistry of carbohydrates, the structure basically. So the subtopic for today is glycosides. Now this is a diagram that shows you the basic structure of a glycoside. Now a glycoside basically has two structural parts. Now the first part that you will see is the carbohydrate or the sugar part or the glycone part. The other part you see or region you see is the A-glycone, and the A-glycone is the non-carbohydrate part of a glycoside. Now, glycosides. Now, what are glycosides? Glycosides are compounds containing a carbohydrate and a non-carbohydrate residue in the same molecule and are bonded by a glycosidic bond. Now, like I earlier said, a glycoside has two major parts. The first part is the carbohydrate part, and second part is the non-carbohydrate part or residue. Now, these two parts come together, and for them to stay together, they are being bonded together by a glycosidic bond. Another way you can define a glycoside is by saying glycosides are defined as any compound that contains a carbohydrate molecule that is convertible by hydrolytic cleavage into sugar. Now the sugar part is called the glycone, like I earlier said, and the non-sugar component called the A-glycone or the gene. So what this is trying to tell you is this: it's saying that when you look at this basic structure again, that there's a way that you can break it down. Now to break this structure into two monomers or two moieties is by passing it through a hydrolytic reaction, and most times we use an acid for such hydrolytic reactions. Now we have some biomedical importance of glycoside. The first we have here is the digitonin. This is one of the most popular glycoside. It's used as a cardiac stimulant. It's also used for treating some variety of heart disease like arrhythmia, which is when the heart rhythm is not properly beating how it should be. The second we have is fluoxetine. Now this is used to produce renal damage in experimental animals. Another one, number 3, we have is alcoholic glycoside, such as salicin, which is involved in anti-inflammatory and analgesic actions. Now, this salicin is one of the oldest glycoside that was ever discovered. It wasn't the first, but one of the oldest. Number 2, we have thioglycoside, such as thiocyanate, and this is involved in allelopathic and antiseptic effects. Thioglycosides are basically glycosides in which an oxygen atom in the structure has been replaced by a sulfur atom. Next one we have is glycosides that are found in many drugs, e.g. in antibiotic drugs. And what you find here is streptomycin. Now, streptomycin, you can say it is an antibiotic glycoside, Next that we have here is anthracycline glycosides. Now, the anthracycline glycoside are majorly of two types. We have the guanidinosin, which is used to treat leukemia. Leukemia is blood cancer of the blood, to treat it. And the other one we have is doxorubicin, which is used to treat a wide varieties of cancer, such as breast cancer, cancer of the bone, and other regions of the body. Now, the next thing we are looking at are the types of glycosidic bond. Glycosidic bond can be described as two types. The first we have here is the beta glycosidic bond. That should be number one. That's the beta glycosidic bond. And the other one we have is the alpha glycosidic bond. Now, as you know, when they say alpha and when they say beta, when they say alpha, what they're trying to say is that at the anomeric carbon, the hydrogen atom will be facing upward, meaning it will be above the plane, while the hydroxide atom will be below or facing down or below the plane. While for beta glycosidic bond, the hydroxy atom or the hydrogen molecule will be facing upwards or above the plane. Just get that basic explanation. Now, looking at the actual 4 types of glycosidic bond, we have 4 of them. We have the C glycosidic bond, the O glycosidic bond, the N glycosidic bond, and the S glycosidic bond. Now, taking them one by one. The first we have here is the C glycosidic bond or the C glycosidic linkage. Now, the C in this statement means carbon. Now, what it means is that the oxygen of reference, the oxygen we're looking at here, has been replaced by a carbon atom. While in the O glycosidic bond, it means that the oxygen wasn't replaced, that the oxygen is still being used to form the bond between the A-glycone and the glycone regions of a glycoside. Number 3, we have the N-glycosidic linkage. Now, for the N-glycosidic linkage, just as the others have followed, the N stands for nitrogen. So what it means is that the oxygen of reference in this particular structure has been replaced by nitrogen. While for the S-glycosidic bond, like I earlier said, has been replaced, the oxygen here has been replaced by sulfur. They are also called thioglycosides. So just note them, they are very easy to remember. CONS, cons. That can be an acronym for you to remember. C, carbon, O, oxygen, N, nitrogen, and S is for sulfur. The next thing we have here is the formation of glycoside. Basically, glycoside are formed from a single sugar and another compound by the replacement of a hydroxy group on the sugar molecule. So what this statement means is this: to form a glycoside, you need 2 things. First, you need a sugar and a non-sugar. Now, at the anomeric carbon of the sugar, you have a hydrogen moiety and an hydroxy moiety or entity. Now, to form this, the hydroxy of this sugar will be replaced by the A-glycone or the non-carbohydrate parts, so they can link together. So I'm taking this step by step. Number 1, the anomeric carbon of a sugar is hemiacetal. Now, hemiacetal will refer to aldehyde sugars, while hemiketal will refer to ketone sugars. Number 2, the hemiacetal can be transferred into a full acetal by the treatment with acid and alcohol, and the resulting product is called a glycoside. So what is saying, like the word hemiacetal, hemi means half. So the sugar will bring in half, while the A-glycone part to bring the other half, and when they form a bond, which is the glycosidic bond, from the glycoside, they end up forming an acetal, a full acetal. So this is a glycoside formation equation. Now, let us take this step by step so you can really understand the message I'm passing to you. Okay, So for what you have here, what you have at your left hand side, this is the sugar. You get it? Now this sugar will be reacted with acid. Now this H plus represent the acid. You can use H2SO for any other acid. Why these parts up here represent the alcohol, the CH3, the CH3, CO2OH represent the alcohol. So when the acid and the alcohol react with the sugar, they combine to form a glycoside. So if you look at this, carefully, you will notice something. And what you will notice here is this. Let me change here. Is this? You will notice that the OH of the anomeric carbon has been replaced by a different entity entirely, and this entity is coming from the A glycone part of a glycoside. So there are some things you need to note about glycoside. The first thing is that the non-carbohydrate residue present in the glycoside is called the A glycone. So like when they say, whenever you see A, it's like saying against. So a glycone is the sugar, while the A glycone is not the sugar. It's something else, but not the sugar. So the point 2, the first ever discovered glycoside is called amidilene. Now, amidilene is a cyanogenic glycoside. Now, cyanogenic is poisonous. It causes cyanide poisoning. Amidilene is very lethal. Now, so this was actually the first glycoside that was ever discovered by a man. You can't remember his name right now. So the next point we have is this. Now, look at this carefully. Now, you have a glycoside. Now, this glycoside that you have here will undergo an hydraulic or hydrolysis reaction to give you a glycone and a glycone. This is the first part, and the second part. So when you break down the glycoside, you have the glycone and the A glycone. Now, give you an example now. For example, the hydrolysis of glucovinylene, a glycoside, gives glucose and the A glycone, which is called